Hey guys, Neutron Star here, and in this video I'm going to make an interesting chromium-based coordination complex, potassium trioxalatochromate. This compound is a water-soluble metal oxalate complex and exhibits a peculiar visual effect known as pleochroism. It's worth mentioning that the method I'm using to make it in this video does not involve any hexavalent chromium, or chromium 6+. The more common method uses a mixture of oxalic acid and potassium hydrogen oxalate to react with potassium dichromate. The oxalic acid will reduce the chromium in potassium dichromate from its 6+ state to its 3+1. However, hexavalent chromium is among the last chemicals that I want to work with. Its compounds are not only corrosive, acutely toxic, but also carcinogenic. Therefore, I decided to try making it directly using a chromium 3+ compound via ligand substitution. This method is both safer and more environmental friendly. These are the reagents used in this video: oxalic acid dihydrate, chromium trichloride hexahydrate, and potassium hydroxide. Before I move on, I just want to quickly mention that I've been an independent music producer this whole time while I'm making videos on this channel. And the music you hear on most of the intros and outros are actually composed by myself. With that being said, I would really appreciate anyone who'd like to check out more of my music, or even support it with a few bucks. My music can be found on Bandcamp, link in the description. To start off, I weighed 8.9 grams of chromium trichloride hexahydrate. Then I added in about 50 milliliters of water for it to dissolve. This will be the first ingredient for the reaction. To make the second ingredient, potassium oxalate, I just need to neutralize potassium hydroxide with oxalic acid. I weighed about 11.2 grams of potassium hydroxide and dissolved it with some water. By the way, I just made a mistake here, and it's not recommended to dissolve potassium hydroxide this way since it does generate a lot of heat in a small volume, and it's better to add the solid into water instead. Next, I weighed out 12.6 grams of oxalic acid dihydrate, and I topped it off with the potassium hydroxide solution. I stirred the solution with a glass rod and occasionally added in more water until everything has dissolved. When everything's ready, I transferred the potassium oxalate solution all to a round bottom flask in a heating mantle, since in the next step I'm going to heat the mixture of the two reactants for a long period of time. I decided to just attach an empty condensing column on top of a round bottom flask so that water in the mixture could still evaporate, but more slowly. I then turned on the stirring and then dumped all the chromium trichloride solution into the flask. After turning on the heating, everything I need to do should be just to wait. However, to my surprise, a few minutes after the heating has started, I stopped hearing the sound of my stir bar, and when I turned to look, a purplish-gray precipitate has formed and everything seemed to have clogged up on its own instantaneously. I think the precipitate will most likely to be chromium 3 hydroxide that has somehow formed due to a temporary disequilibrium in the reaction. I tried poking it around with a glass rod until the stir bar could function again, and it just seemed to have magically disappeared again a minute later. Overall, I should have just added the trichloride solution gradually. I'd quickly explain what I'm trying to do here. When chromium trichloride dissociates in water, a complex forms between the chromium 3+ ion and water. In this complex, water molecules act as ligands, which have lone pairs of electrons that would fit into the chromium. However, with oxalate ions present, we could substitute the water with oxalate ions, which also act as ligands, and the overall reaction looks like this. However, this process could be notoriously slow and inefficient for chromium 3+, so long hours of heating and stirring is required. You could do this with any chromium 3+ salt, and it's better to use chromium sulfate though, since the side product potassium sulfate form has a lower solubility and therefore easier to filter off. But I just happen to have chromium trichloride on hand, and purity is not really my first priority. I checked on the mixture 2 hours later, and when I shook it around, I was a little unhappy to see that it has this dark blue color. From what I've seen in the previous test run, the final solution of potassium trioxalatochromate should be dark purple. But to see that if I even made the right thing, I took a small sample of the solution and shot it into some water. I immediately saw the iconic color of potassium trioxalatochromate solution, which isn't well captured by the camera. The color of its solution is strange in a way that when looked directly it's purple, but the color turns bluish-gray as you look away. Despite this, I was still afraid of the reaction being incomplete, and to push the reaction equilibrium to the oxalate complex side, I just added in random amounts of excess oxalic acid. I let it run for another hour, and when it's done, I can see that the solution has turned dark purple. Then I transferred it to a beaker for further evaporation. When solid starts appearing, I poured all the liquid into a smaller beaker to crystallize, but I kinda boiled it down too much, and instead of crystallizing, the whole thing solidified. Here you can see the color of potassium trioxalatochromate as a solid, which is dark green and nearly black. When I added in some water, the solution might seem black, but things get interesting if I put the beaker under sunlight. You can see the true nature of the liquid, which is a translucent color of red. From what I've seen, the red color starts to emerge only when the concentration of the solution gets to a critical value. I put this solution back to the heating mantle, and once it has all redissolved, I poured the entirety of it to a crystallizing dish and waited for crystals to form. Only a few hours later, I can already see a decent amount of black crystals forming in the solution. And here is when you can see the three colors involved in the solution of this magical coordination complex. Now I feel it's time to demonstrate pleochroism, which basically means different colors when looked at different angles, in the crystals of this substance. I found the colors of large crystals being extremely dark, and I can't see an explicit color even after shining a strong light onto it. Instead, different colors could be seen better on smaller crystals. Notice how the color of this tiny piece of crystal changes when I turn the crystallizing dish. However, it was said on the internet that these crystals have three colors, and I don't know exactly if the crystals I have here is just too dark to see all the colors. The larger crystals also have a translucent color of red, which is the same with this concentrated solution. Now, although I've demonstrated the fascinating multitude of colors of potassium trioxalatochromate, I don't really know the mechanism behind all these optical effects. If you, dear viewer, know some theories in this specific field, or have noticed anything I said in this video that is wrong, feel free to comment down below. I've also found a way on the internet to sort of dilute the color of this complex, and that is by making a small amount of it with another colorless complex, potassium trioxalatoluminate, which is basically the same thing except swapping the central metal ion from a chromium 3+ to an aluminum 3+. This way it would be possible to observe the complex pleochroism better, and it's going to be for the next video. That's all for this video, thanks for watching, and I will see you on the next one.